Hello, welcome back to our little corner on the web, where we go through math problems to hopefully encourage and nurture interest in math. Today, we will go over questions 4, 5, and 6 from the 26 PMO area stage, part 1. Question 4. How many ordered pairs of positive integers xy are there so that the set xy135 has a unique mode and the arithmetic mean, median, and mode have the same value? Okay, so given how the question is set up, where we have xy135 and a unique mode, there's really only a few possibilities for the mode, right? One is when x equals y, so basically x will be the mode, or the mode has to be 1, 3, or 5. So for this case, let's look at the case where x equals y first. Some of you might be able to eyeball this, but let's go through it rigorously. So when x equals y, the mean, right? The mean will be 2x plus 1 plus 3 plus 5 over 5. And that should be equal to the mode. So the mode that we have is x, right? So 2x plus 9 equals 5x, or 9 equals 3x, x equals 3, and that's also equal to y. So one case, when x equals y, so case 1, I'll put it here, xy is just 3, 3. Okay, and that deals with mode equals 3 as well. Okay, so we know that we don't need to deal with mode equals 3 anymore. So the only cases left is mode being 1 or 5, meaning one of x and y is 1, the other could be a different number, and one of x or y is 5, and the other could be a different number. So hopefully it hopefully will also occur, obviously, that when x, let's say, is equal to 1, and mode is 1, and median is 1, then to make the average also 1, y will be negative, which actually violates what we have, that both x and y are positive. So here, there's no case, right? No cases possible. Okay, because we also want the average to be 1. Okay, so the only thing left is when x equals 5 or y equals 5. So there's two cases, right? We'll only do one because the other one will just be the flip of the cases. So when we want average to be 5 and equal to x, then we have 5 plus 1 plus 3 plus 5 plus y, right? All over 5 is equals to 5. Okay, and with a bit of manipulation, you should be able to get y is equals to 11. So another case is 5 comma 11, and flipping x and y, we also get 11 comma 5. Okay, so since there's no cases anymore for mode equals 1, and we have the mode equal 3 being x and y being equal, then we only have these 3 cases. So the answer for this one is 3. Okay. So moving on to the next question. Okay, question 5. A stack of balls in the shape of a triangular pyramid contains 2,024 balls. How many layers does it have? Below is an example of a triangular pyramid with 4 layers. So each of these layers here is forms a triangle. Okay, and it's formed by the first layer being 1, the second layer being 1 plus 2, the third layer being 1 plus 2 plus 3, the fourth layer being 1 plus 2 plus 3 plus 4, and the nth layer will be the sum from n to 1 to n. Okay, so notice that each layer, we can write it here first, the first few at least, 1, 3, 6, 10, 15, 21, and so on and so forth. Notice that each adjacent pair is actually a perfect square. The sum of them are perfect square, meaning this is 4, 9, 16, 25, 36, and so on and so forth. So we have the sum being 2024. There's two cases here. One, it could have an odd number of layers, or it could have an even number of layers. So we'll tackle the even number of cases first because they're easier. If it works, we're done. If not, then we tackle the odd number of cases. So if it's an even number of layers, what we'll actually have is basically four here, 16, 36, and so on and so forth. If it was an odd number of layer, what we will do is we'll take one separately, 9, 25. So basically the sums of the odd squares. Okay, so if there's an even number of layers, we can just take the sum of the even squares. So first, let's just assume it's even, and if it doesn't work, as I said, we switch. So if it's an even number of layers, then we have 2 squared plus 4 squared plus 6 squared plus ... some some 2x squared. Okay, we can rewrite that. Oh, and we want that to be equal to 2024 if we can find such an x. Okay, so we can rewrite that as 2 squared times 1 squared plus 2 squared plus 3 squared plus x squared. So this is no more than the sums of squares. So we have 4 times x plus 1 times 2x plus 1 all over 6 equals 2024. Okay, this x times x plus 1 times 2x plus 1 all over 6 is basically the identity for sums of squares. Manipulating this a bit, we get x times x plus 1 times 2x plus 1 is equals to 3036. Okay, so just taking the largest terms, and I'll sort of scribble here on the side, we know that 2x cubed, the highest order term for x, should be less than 3036, but close to it. Okay, so we know that x is in the teens. X also can't be 10, because if it was 10, then this product here, the x times x plus 1 times 2x plus 1 will end in a 0. Okay, and 2x cubed, when x is 12, actually is over 3036. So the only possibility that we need to test, right, is test for x equals 11. And sure enough, 11 times 12 times 23 is equals to 3036. So basically, we found our x. But note that here, we denoted the number of layers as 2x. So n is equals to 2x equals 22. Okay. So the answer for this question is the number of layers is indeed 22. Okay, so we'll move on to the next question. Okay, question 6. What is the greatest number of checkers that can be placed on the squares of a 26 by 26 checkerboard so that each unit square contains at most one checker? Each checker lies entirely inside one unit square, and no 4 of them lie on the same 2 by 2 square. The most straightforward way probably of answering this is actually to solve for the complement, meaning the number of squares that are empty. Okay, so if we assume that we start with a checkerboard 26 by 26 that's completely filled, okay, completely filled. Okay, so actually I should erase part of it because it's ... I'm not going to draw all 26. So, okay, and same thing for for here. So what you're gonna, if you assume that this is completely filled, what we really need to do is remove the minimum number of checkers. So just by inspection, we know that we want all of the top to be filled. So we'll remove this. That makes this 4x1 here, 2x2 here, satisfy the constraint. The next one we would remove is here so that we minimize, and the alternating one. So in this row, we will end up removing 13 checker tiles. Yeah. So again, to minimize what we're going to remove, we're not going to remove anything here. So every other line, we will remove 0. And every other line, we will remove 13 in an alternating pattern. Okay. This is the minimum number of tiles that we can actually remove. Okay. So the rest will remain in there. So if we just count the number of tiles we will remove, there will be 13 per alternating rows. And since there are 26 rows, we will be removing 13 tiles in 13 rows, or we will be removing 169 tiles. The total number of tiles when we started, because we were trying to solve the complement, was 26 squared. So in essence, it's 26 squared minus 13 squared, which is just 676 minus 169, or 507. Okay. So the maximum number of checkers that can be placed is 507. Okay. Hopefully these solutions were useful and educational. If they are, do hit the subscribe button and the like button. Thank you for watching.